Hello, everyone, and welcome back to our next UEI Masterclass. Last week's was very successful. There were many follow-on conversations. It's really great what our team is putting together. I hope everybody is weathering the current epidemic or pandemic. I know I am broadcasting to you from down in my basement. It's tons of fun. I am Eric Ertet with UEI. And today we will be doing an introduction to MIL-STD-1553, the avionics bus, and getting started with programming. This is meant to be somewhat informal with a Q&A session after each topic to cover various concepts. Here is your quick agenda. So first thing we're going to do is just have a general overview and applications tutorial, and then answer any of your questions. Then we're going to jump into looking more at 1553 solutions from UEI, BCRT, and BM, and open that up for a second round of questions. And then we're going to show you how to get your data quickly and easily. And then, of course, have a bunch of questions after that and wrap it up. So your questions can be asked on the chat box in your lower right. Please enter them as you go. We will be reading out those questions and answering them, so please keep them coming. On hand will be your resources, the UEI applications team right here. Up top, we've got Timor, who wanted everybody to live dangerously and use auto set on your oscilloscope. Next, we have Austin Turner, who has been an applications engineer here for more than 5 years with expertise in embedded devices, hardware and software, and is an avid hiker, but a terrible flight simulator pilot, apparently. Next, we have Brian, who is our friendly, experienced, helpful support engineer. His favorite customer is a happy one. And his statement is, there's no such thing as a stupid question. Next, we have Phil, who has worked in the automation and embedded industries, helping customers select and deploy technology around the world. He certainly agrees with Brian. Knowledge is built on asking a question, and every single question is worthwhile. Then we have Prabhu on the other side of the pond in the UK. He really has nothing to offer but solutions, workarounds, and fixes. His mantra is keep calm and carry on. So this is our team today. And we are lucky to have Phil to be reviewing all of these 1553 concepts. So please take it away, Phil.
Hi, everyone. Thank you very much for joining us today. Let me bring up the screen. Okay. Today we're going to talk about some 1553 specifications, how it works, and we'll get into the details of functionality on our I/O board, as well as you'll see PowerDNA Explorer and C code run a complete application. We do support many other languages and interfaces: C, C++, Python, LabVIEW, Simulink, and a lot more. We've planned a series of these sessions, so there will be upcoming meetings focusing on the bus controller, RTSAs, the bus monitor, and getting events to notify your application of what's happening in these systems, as well as the ability to optionally inject errors into the system to stress test the applications. If there's something specific you would like to see us cover in the future, please chat it at the end of this or send us an email. We would appreciate all your input. So when I start the video, you may want to lower your speaker volume. Zoom tends to raise the volume a bit. Our first video is a general introduction to 1553. And let's get started. I'll give you a second to lower the volume.
MIL-STD-1553 is a military-grade avionics bus created over 40 years ago by the United States Department of Defense. First employed in the F-16 fighter, it has since become a widely adopted data bus used in a variety of military and civilian applications for flight, land, sea, and even in space. Why is 1553 so popular? Because it's simple, deterministic, and reliable. Like all avionics buses, the goal of 1553 is to move data reliably. 1553 messages consist of up to 32 16-bit words. There are three major components of the system: a bus controller, or BC, which is usually part of the mission computer, remote terminals, known as RTs, and subaddresses that might be a missile launcher or an instrument giving input to the mission computer, and the bus monitor, which passively allows you to monitor the flow of data. The BC is the only part of the system that can initiate a data transfer. This leads to 1553's reliability because there are no bus contentions with multiple controllers trying to transmit data. It's military grade, meant for life-critical applications. It has a simple, provable design and redundancy for safety. The bus consists of two sides, commonly labeled A and B. If a reply does not come back in a fixed amount of time from side A, the command is sent on the other side of the bus, side B. 1553 uses a fixed set of commands. The most common are BC to RT, which means the bus controller is going to send data to a remote terminal. For example, a command to fire a missile. The command RT to BC is a request to have the RT send data to the bus controller. For example, information from an avionics instrument. There is also an RT to RT command. This is used when the bus controller commands one RT to get ready to receive data, then commands another RT to transmit the data to the receiving RT. Now that we've covered these commands, let's take a look at how they are transmitted. MIL Standard 1553 comes with a built-in scheduler. This scheduler consists of a major frame and multiple minor frames, allowing you to talk to different RTs at different frequencies. Imagine a scenario where you have an instrument that you need to talk to once a second, another instrument 5 times a second, and a third at 10 times a second. How could you set this up? So for the first RT, you put in one minor frame. If you need to talk to a second RT at 5 times a second, you put in 5 minor frames. And the third RT at 10 times a second, you put in 10 minor frames. You're not limited to 1, 5, or 10. You can put in any number of minor frames for a particular RT. Let's take a look at some of the common commands that could be transmitted by the bus controller. Here is the sequence of events for a BC to RT command. And here is the sequence of events for the RT to BC command. And here is the sequence of events for the RT to RT command. If we actually take a look at the signal on the bus, looking at the lower two lines, you'll see the bits are half high and half low. This is known as Manchester differential encoding. All this adds up to an avionics bus renowned for its simplicity and its reliability. The only component in the 1553 system that controls all data transfers is the bus controller, which is tied to the mission computer. It has dual buses for redundancy and safety, side A and B, and a fixed response time for all replies. One of the most popular variations of MIL Standard 1553 is A-Ring 708. A-Ring 708 is based on the same physical lines and encoding as MIL Standard 1553, but 708 is used for weather radar. The length of the data words is the primary difference between the two. Messages in A-Ring 708 are much longer given the amount of information a radar image may have. It also allows data to transmit on both sides of the bus at the same time. Looking toward the future, 1553 is in no danger of being phased out. New applications like unmanned aerial vehicles and smart bombs all take advantage of the deterministic, redundant, low-latency 1553 architecture. And new specifications are emerging to extend 1553, like faster bit rates to allow more data to go through the system, a must for next-generation equipment. Not bad for a piece of technology that's over 40 years old and going strong. Learn more about technology.
Okay. So we have a few questions. Question is, does the UEI 1553 IO board support all the commands of the standard? The answer is yes. We are tested to AS4111, and so that verifies that all the required commands are supported and done correctly. Okay, let's take a look at the specific functionality on our IO board and how a complete application is run.
Hi, I'm Phil, an applications engineer here at United Electronic Industries. UEI provides support for all the major components of MIL Standard 1553, RTSAs, bus monitor, and the 1553 major and minor frame scheduler, or bus controller. We've also engineered a bus writer. It is a FIFO-based scheduler and does not require you to use major and minor frames. The bus writer will simply send any of the standard 1553 commands when you need it to. The bus writer uses the PC CPU. For more deterministic behavior, you can use our API to program the FPGA on our I/O board. Our API allows you to access the complete functionality of all 1553 components through many programming languages. However, to provide you with an easy-to-use interface to exercise this functionality, we've created a graphical utility which is installed for you when you install our PowerDNA suite of software. This utility is called PowerDNA Explorer. Let's take a look at how easy it is to use. When PowerDNA Explorer powers up, it scans a range of IP addresses to find the cube or rack. The range of addresses is configurable. As we can see here, PowerDNA Explorer has found the IOM, the cube or rack, and has identified several boards that are available to us. When I click on the 1553 board, I can configure the board and run it. We see two channels. Each channel can be all RTSAs, a bus controller, a bus monitor, or a combination of RTs and bus monitor, or a combination of bus controller and bus monitor. Today I'm using a 1553 loop-back dongle, which is supplied with our 1553 I/O board. The dongle we are using loops channel 0 to channel 1. So I will configure channel 0 to be the bus writer, and channel 1 to be RTs and a bus monitor. Now that I've added a bus writer, I'll add a command. I have a choice of the standard commands, but I'll select BC to RT, I'll select RT8, and SA7. I can send up to 32 words, so I will send 32, and I can have the system increment the words, so each successive word is different. I can then set the bus writer to send this command periodically. The default is 10 milliseconds, which I'll accept. I'll now configure channel 1 to be RTs and a bus monitor. You can see at the top it says select remote terminals to monitor, and I'll enable all RTs. The next section enables the RT itself, and I will select all RTs and all SAs. Now I'll simply start the system and look for the data transfers. So as you can see here, a BC to RT command, a receive command, is being sent from the bus controller to RT8 SA7, and it's 32 words. Now a nice feature of the system is that you can ask PowerDNA Explorer to automatically increment each data word on each successive command. therefore seeing data change with every command. As you can see here, this starts at C7, the next message starts with C8, and the next with C9. So I've just demonstrated PowerDNA Explorer, a graphical utility that allowed me to configure in less than 60 seconds a bus writer to send 1553 commands, all RTSAs in the system, and a bus monitor to show you the data. Simply plug in your external device to one of our channels, and you're off and running. Got a question or want to talk about your specific application requirement?
Okay, sorry about the brief interruption from support. Let's take some questions. So does 1553 require cable termination? Yes, it does. And does PowerDNA Explorer support the Mac or Linux? It definitely runs on Linux. I'd have to check on the Mac. A few of our sales engineers have them. I haven't personally used it, but I will check. Get back to you. Question is, you seem to have a mode where the program runs on a PC. Do you have a standalone mode? The answer is yes. We have a PowerDNA mode where the program runs on a PC and is tethered to the cube or rectangle. And we also have a UEI pack mode, which is a standalone embedded controller. And it can run every 1553 program in either mode. The standalone controller can boot Linux or VxWorks. Is PowerDNA Explorer an extra charge? No, it comes free in the PowerDNA software. Next question, where can we get the software? It's available on our website under software downloads. There's a Windows version and a Linux version. And then, are there loopback adapters available for other I/O boards? There are. Just contact us. I think that's it. Okay, let's go to our last video.
Hi, I'm Phil, an applications engineer here at UEI. UEI's extensive product catalog supports many avionics buses, including 1553, 429, 708, and AFDX. Now we're going to take a closer look at 1553. UEI supports all three functional components of a 1553 bus. These components include the bus controller, remote terminals, and bus monitor. The bus controller is the only thing in the system that can initiate bus traffic. It does so by sending commands. It might send a command for an RT to receive data, or a command for an RT to send data. There can be up to 32 RTs in the system, each with up to 32 subaddresses. So for instance, an RT might be a missile launcher, and each subaddress might be a particular missile. The bus monitor does what it says. It simply monitors traffic on the bus without affecting the system. Each I/O card has 2 channels, and each channel can be a bus controller, an RT, actually up to 32 RTs, or a bus monitor. In addition, you can combine the bus monitor with an RT on a channel, or combine a bus monitor with a BC, a bus controller on a channel. Thus, you have a lot of flexibility with just one I/O board. The architecture of the UEI components and API easily allow you to take data from one of our sensor-based I/O boards and put this data into the UEI 1553 system to simulate avionic input or output devices. So as I look at this sample, you'll see it's one C file. We can bring up this program and we'll run it. What I have is a loopback dongle that ties channel 1 to channel 0, so we can see traffic on the bus. I'll stop and we'll look at the output. The sample's set up so that the bus controller sends a receive command to the remote terminal. So the bus controller is trying to send data to the remote terminal. The data is received by the remote terminal. The bus controller sends a transmit command to the remote terminal, which indicates the remote terminal should send the data back. And then we have the data received by the bus controller. We also have bus monitor data. This is the raw data. And we have a function that can be called to format the data. And indeed, you can see a receive command sent out, the first command, and a transmit command sent out, the second command. All this with a single file. So with this one sample program, you have an amazing amount of functionality that you can tap into right away. UEI supports a wide variety of data acquisition sensors and avionics buses for military and commercial aircraft, as well as for weapon systems, ground vehicles, and space applications. Please contact us to discuss your particular application requirements.
Okay. So let's answer a few more questions. Can I take A-Ring 429 data and send it out the 1553 I/O board? Absolutely. You can have a 429 card in the cube or rack with the 1553, and the application can easily see input and output from both and send the data both ways if you wish. How independent are the two channels? Well, they're completely independent. We have an FPGA on the I/O board, and each channel is basically a mirrored copy with no connections. So it is completely safe to run one channel on one 1553 system and the other channel on another 1553 system. They're completely independent. What API does PowerDNA Explorer call, and is that API available to us? Yes, it's available to you. It's our point-by-point API, and that's what sample 553 is built on. All this, the PowerDNA Explorer, the C code, and many more 1553 examples all exist in our PowerDNA software that is available on our website. If you want to email us, I can send you a link directly to it. By bus writer, do you mean bus controller? Well, let's define a bus controller as an intelligent way to send messages and auto retry. So we have the major minor frame scheduler that will send multi-rate messages on specific time boundaries if you wish. And if it does not get a reply on side A, it will retry on side B. So that would be a bus controller. The bus writer's function is to send a command. Any command you want, or series of commands. It does not auto retry. So those are the real differences. Besides the I/O board, what else is in the chassis? So each cube or rectangle has a CPU and power board, and then all the I/O boards you choose to put in it. Do we have a different 1553 I/O board for each chassis? No. We have one circuit board with different carriers for the different chassis. I think that's all the questions. So that covers the material we wanted to do today. We will definitely have more sessions diving deeper into the bus controller and the different components, how to use the RTSAs, how to inject errors. And we would really like to hear from everybody on what you'd like to see in the future, not just for 1553. Technology, we're going to do IoT shortly. Sensors, what sensors do you use? Any more on avionics that you'd like to see? We're planning to do 429 and some more on 1553. So we would really appreciate any input you'd like to send in. So I'd just like to say thank you very much for joining us today. And have a great day.
Well, thank you, Phil. That was great. And thank you, everybody, for participating. Please send us your questions. Send us what you'd like to see in the future. We really enjoy talking about many of these different topics. We will be contacting anyone with unanswered questions or partially answered questions. Certainly, if you have more questions or need anything, there is our email address, support@ueidac.com, or the phone number. The best at this point would be email, as in I think everybody is working remotely. We will be continuing this masterclass series at the same time next Thursday. We're going to push out a couple more about IoT edge computing and the Guardian Advantage for the rest of April. And then May looks like it is avionic month. So we will cover a lot more 1553 concepts, from air injection to advanced programming and scheduling, and we'll even cover some AirInc 429. Until then, everybody, please stay healthy, and thank you.